Thank
Thank you
you.
very much. Hi, everybody. My name's Tom, co-founder and CEO of Wase, and we are unlocking the power of waste to make it the field of the future. And what we're doing is a presentation now looking at specifically the food and beverage production organizations and how we can support those. So water, energy, and food are our most valuable resources, but particularly water is one of the most undervalued. Quite consistently, we are polluting it every single day, but it is really the essence of life and why we're all here, and it is a really key component to all of food and beverage production. And what we want to show is that wastewater can recover valuable water to be reused. We can recover the energy and we can recover nutrients. So we can put it back into the environment. So at Ways, we believe in building a sustainable world where our most precious resources are valued and protected. And we're doing that by helping businesses to unlock the power of their waste so we can accelerate a net zero journey. So during the presentation, we're going to discuss the opportunities for food and beverage companies to look at decarbonizing their energy, maximizing their resilience by unlocking sort of the energy that is within sort of bioresidue and wastewater, so that you can then look at increasing your bottom line. So, what are the challenges for the food and beverage? So, I'm going to be speaking to the choir here, but you have like high volumes of wastewater and bioresidue. There is a high cost for effluent disposal. There's a really high thermal energy demand. There's a desire to be more sustainable, but quite often a lot of the facilities have really limited space for new solutions to be integrated at their site. So if we look at the sort of typical wastewater treatment options that are available to the food and beverage organizations, we have disposal to sewer, if you're able to do that. You could have on-site aeration treatment. You could have collection by tankering to have it hauled off site, or you could have on-site anaerobic digestion. So we're going to go in and explore these later. So looking at discharge to sewer, this is quite a low cost, simple solution if you're able to do it. But there are sort of increasing discharge regulations and permits that to discharge what you can put down the drain. And quite often you'll need to take and segregate quite a lot of the high strength wastewater. There is also potentially risk of fines that we see for some of our customers where they might get influx of sort of high COD wastewater. So having something on site can sort of really build in a much more resilience. Discharging to sewer is also has quite a big impact. As many people know, the UK is 2% of their energy demand goes on sort of wastewater treatment at utilities, and this is because they're based on sort of aeration processes. And when you're adding sort of higher strength wastewater that you get from the food and beverage sector into the sewer, you're actually diluting that higher strength wastewater with a lot of rainwater and other types of wastewater that then dilutes it. So it makes it much more energy intensive to treat because you're treating a sort of a much higher volume of dilute waste. It then can emit greenhouse gases in the sewage line. So there's new research looking at sort of the methane that can be emitted because it is being broken down anaerobically in the sewage treatment line. And on days where we have really heavy rainfall, there is a risk that it could get into the environment as well. So if we look at tankering, which is really common within the food and beverage sector, to take off sort of that higher strength wastewater that can't go, or bioresidue that can't go into the sewer, or be treated through sort of on-site treatment. Typically, we see our customers doing like 1 to 7 trips a week. That might be like 50 miles per journey. So it could be 2,600 to 18,000 miles a year that they'll be traveling. So if you were tankering 7 times a week and doing 18,000 miles, that's the equivalent of driving a truck from Bristol to Ghana, South Africa, Kenya, and all the way back home. So that is a huge amount of distance that is traveling and driving that waste around the organization. I'm assuming you want to drive all your food products around that way, but not your wastewater. To do this, you're probably paying over £100,000. You're emitting 22 tons of carbon and you're using 8,000 litres of diesel. But really importantly, you're driving away about 300 to 400 megawatts of renewable energy that you could recover on site using the right solutions. Using aeration type technologies, it's quite a low cost solution. It's quite simple sort of to operate, but you do have to be aware of the bacteria and the biology within the system. It's good for sort of lower strength sort of COD waste water, but it does have a bigger environmental impact because it is quite energy intensive. You have quite sort of tried and tested technologies. So a lot of organizations have DAF systems, but you have quite high chemical usage with DAF, and you generally generate high volumes of sludge as well, especially where you're adding polymers into the process that then needs to be tankered and hauled off site. You then have like moving bed biofilm reactors, membrane bioreactors, and membrane aerated bioreactors, all getting sort of increasing in efficiency, but also increasing in sort of cost. But one thing with anaerobic treatment is you always do generate high volumes of sludge, and these are really good for sort of targeting um, lower strength sort of wastewater treatment. So just recapping, you have sort of lower cost, a high cost, capital cost for sort of aeration treatments from like DAF being very low cost, MABRs being a much higher cost. You have the high energy demand, the additional chemicals, and you generate sludge. So if you want to look at transitioning to circularity, to treat sort of your wastewater on site, recover bioenergy, so you can sort of meet the regulations, look at recovering nutrients, also looking at recovering and reusing water and reducing your carbon, you probably would want to start looking at alternative technologies or having a part of a train of technologies where you would look at recovering energy using anaerobic treatments, where you can then recover the energy from the wastewater and also the bioresidues and sludge that you might be generating. Typically, depending on the process, it will have a slightly larger footprint than an aerobic process, but you do generate a lot lower amounts of sludge. So the typical plants are a typical anaerobic CSDR, so continuous stirred reactors, which you can sort of see in the image below. These are really good for sort of very high sort of solid wastewater streams. And then you have your upflow anaerobic sludge blanket systems, which are used for sort of lower strength COD wastewater. And you need to make sure you remove like a lot of the suspended solids from this system because you have a granular bed within that process. And if you have too many solids within there, that can float out the granules and you'll need to reseed those processes. So they're much more suited for larger sort of organizations where you have a very sort of stable wastewater stream that isn't very high in strength. Now, there's a new sort of next generation of technologies coming out that form under bioelectrochemical systems. So within this, you have microbial fuel cells, microbial electrolysis cells, and electromethanogenic reactors. Microbial fuel cells use bacteria to generate small amounts of electricity, and it can provide more of like an energy neutral wastewater treatment. Microbial electrolysis cells, they also can be used to generate hydrogen. You need to have membranes within the system, so you do lose some of the efficiency and you increase some of the maintenance of the process. And then you have electromethanogenic reactors, which I'm going to go into a bit more detail, where it's a membraneless technology, so you can treat sort of lower strength wastewater to high strength wastewater with quite high solids content up to 7%. So if we look at sort of anaerobic digestion and sort of look at the differences compared to the electromethanogenic reactors, with anaerobic digestion, you have a giant tank where you grow sort of bacteria and you have like organic waste going into the reactors. During that process, you go through 4 stages of breaking down the organics from the sort of more complex organics into methane. And during that process, you generate biogas about 50 to 60% methane concentration. Because you've got 4 stages of this treatment, you do have sort of competing reactions within the process. Because the bacteria are just in bulk liquid, you have to have quite long retention times to make sure you don't flow out the bacteria. So this is why it's really only suited for sort of like larger sort of continuous stirred systems for higher strength wastewater. And that's why they have quite a large footprint to make sure you have good residence time and you don't throw out the bacteria. What we've developed is a new bioelectrode technology where we integrate that into an anaerobic reactor. And this means that we can grow biofilms on the these electrodes, and we can accelerate the breakdown of organic compounds, and we can have much faster throughputs because we can break down the organics quicker, but we also have a fixed biofilm. The process also increases the gas quality and the gas yields. So we generate biogas with about 70 to 80% methane on some of our feedstocks, and we reduce the amount of organics within the wastewater. So the way it works is we grow electroactive bacteria on these electrodes, and they form biofilms. And what they do is, as they break down organic compounds, they release those electrons from themselves onto the electrode surface. We capture those electrodes and we supply a small potential to direct the flow of those electrons. And that means we can start generating hydrogen ions inside the reactor and convert carbon dioxide fraction of the biogas into methane. So this is how we get high quality gas compared to a standard anaerobic digestion system, and we can also increase the yields. This means that it's much easier to integrate into existing boilers that you might have on site. It can also help improve the efficiencies of a CHP system as well. Compared to anaerobic digestion, we typically see that we can treat the wastewater about 3 to 10 times faster than standard processes. We can have sort of the organic loading rates that you might get with an upflow anaerobic sludge blanket system, but with a much higher sort of solid content that you don't need to remove, so you can extract more energy. And we typically see about 30% higher energy yields. We get a 30% increase sort of treatment and COD removal from the wastewater. We then have a really key aspect is our AI biosensing automation platform that we integrate into the process so that you don't need to have skilled operators on the ground. We can then automate the plant, and which is really important because a lot of our customers that we see is you have quite variability in the sort of the COD, the BOD, and the wastewater. And what you need to do is make sure you have quite consistent amounts of that being fed into the process, so you don't over or underfeed the system. And because it's faster, it's about 70% smaller than a standard anaerobic digestion system. So here you can see a study that we did with GRDF, which is the French gas distribution network, where we looked at sort of the raw feed from food waste that was extracted, and we generated 29% more methane than a standard anaerobic digestion system, and we were able to further validate that we could extract more yield by taking sort of some of the digestate from an existing plant to further break that down and increase the amount of methane that can be generated. This also increases the stability of any digestate that's being spread to land because you're really extracting all of that methane from it, so you can utilize that on site. We also looked at a case study for a customer comparing our process to an MABR system. We found that the CapEx of our system was lower than the MABR. The OpEx was low, and we were able to generate over 1,800 kilowatts of energy a day compared to the MABR using energy for that process. And because it's an anaerobic system, we would generate less sludge than the aerobic process. But it does have a slightly higher footprint than the MABR because you can have a much faster process. So how small can we go? So this is a site that we have at a dairy farm. There we've got what you can see is sort of the dairy shed on one side, and then we have sort of a cliff and sort of with the trees on the other side. So it's a really sort of small area where we had to fit the system. Due to the modularity, we could quite easily put it into this place with still having access and walkways for the customer. Here you can see sort of the pump room, our reactor, and also gas storage on top. And then we have a CHP and a boiler room. If we were to look at a standard anaerobic digestion system, the plant would actually take up the dotted line around here. So for this customer, it wasn't actually a feasible option for them. The system is really modular, and it's sort of like a Lego brick wastewater treatment system. So we've designed the modularity so it can be really fit to your size and we can scale it up. But it also means that you can install a small unit and then increase the amount of units that you have at later dates, that you might want to add new waste streams, you might want to expand. So it gives you a lot more flexibility than trying to design a much larger system, thinking about what you have to do in the future. So now we're going to go through a couple of case studies. So Hepworth Brewery is one of our case studies. So I'm going to introduce you to Andy, founder of Hepworth Brewery, that produce between 20 and 30,000 hectolitres of beer. They produce their own beer, but they're also a contract brewer as well. And Andy is really sustainability driven. He's really put in a lot of effort to look at improving the way that Hepworth can operate, and is really a leader sort of in this space for breweries. He's integrated CO2 recovery on his facility. He's got solar for electric. He's also recovering heat from the fermentation process, and he's now integrating wastewater to energy plant with us. So, like many people, Andy had really high sort of wastewater haulage costs and also energy cost. Wasn't able to discharge to sewer, so he had to have collection of that wastewater every single day to be then treated off-site. He looked at installing an anaerobic digestion system, but because it was quite big, slow, and inefficient and wouldn't meet sort of the regulatory requirements for discharge on site, he would have had to purchase more land as well, and with sort of the areas of where he wants to look at expanding, it was quite difficult to think about actually sizing this kind of facility. So we helped Andy to really look at validating the circularity of our technology, so we could then treat the wastewater, so then it could be like treated and returned back to the environment safely. And there is an opportunity down the line to look at reusing some of that wastewater for sort of cleaning. Then we can look at recovering the biogas that is going to go into a combined heat and power system to provide heat and electricity back to the plant, and it saves carbon. So here you can see our pilot system being installed. This was back in 2021 that we installed this system. So it's got our old branding on it. And I'm going to go through some of the results that we had. So with the one of the key things that we discovered during the trial was the variability in the wastewater strength. So it would go from sort of just below 10,000 up to like 23,000, 24,000 at periods. So there's a huge fluctuation within sort of the wastewater. What we were able to see is that we could provide really good COD removal rates, even though there was that huge fluctuation throughout the process due to the stability of our system. But one thing that is really key to note is when you do have high fluctuations, there is a risk of having high sort of organic acid accumulation within the process. And then that means that you can then build up with acid, you can affect sort of the pH of the system that can affect the bacteria. So typically, you want the phosphatic between 0.2 and 0.6 within the process. So that red band here. Now, if you are having sort of a normal process and you weren't taking constant phosphatic, because you've got that variability in the COD, and if your pumps are operating at the same rate, you then have these huge spikes where you put the system at risk. So during this period, we noticed that if it was a standard treatment system, you would have 11 periods of risks. So that's about 2 to 3 periods per month because of that variability in the COD within the system. We had a person on site constantly measuring the phosphatic. And what we've now developed is a machine learning tool. So we can predict what the phosphatic is in the system completely remotely. So we can then use that to automate the plant and then control the pumping, so that if you do have the spikes in sort of the phosphatic or variability in your COD, the pumps will automatically control and vary the feeding rates so that you then remove these risks of feeding period. We were also able to show that during these sort of high spikes, we could remove the risk, we could provide stable treatment as well. So what this means for you because of the AI biosensing is we can really have quicker processing. We can ensure cleaner effluent. We can maximize the amount of biogas generated, and we can have less downtime. And it's lower operating costs for you because we can really control the system. And that's just one of the metrics that we can work on. We've had sort of 95% accuracy in predicting sort of the COD as well. So we've integrated that metrics into an online dashboard that all your operators will be able to see. So you can look at the uptime, the energy efficiency of the plant, the COD removal, and a key one is the microbial health, which is a key unique indicator that comes from sort of the process of the electrodes being out throughout the whole reactor. And we're the only ones who can give you this data throughout the whole of your process and not just at one sort of single sampling point. So because we had part of the process and also the biosensing, we were able to provide really stable treatment throughout this test, even with this variability of the COD, to then look at quite significantly lower COD between like 1,000 and 2,000 coming out of the system. During the trial, we really looked at optimizing the system. So we were looking at increasing the organic loading rate of the process to look at then optimizing the site design going forward. So we moved from sort of quite low organic loading rate as we were inoculating the system, and then moved up to reach quite a high loading rate. And we were then having quite a low hydraulic retention time between 1 to 2 days, where we found the optimal sort of treatment rates, so we can then design the system that would be suitable for that site. During sort of the increasing organic loading rate, we were able to show that we could generate really stable biomethane concentrations, increasing the biogas methane percentage just over 70% by the end of the trial. Whereas a typical anaerobic digestion test that we did from this feedstock was about 56%. So quite a significant increase in the gas quality for this facility. So what makes up a Wase solution? Here is a diagram of the facility. We have the existing equipment on the site. So we have some initial storage tanks, settlement tanks, and buffer tanks. What we have as our standard system is our reactor. We have a gas storage, which are both in 40-foot containers. We have a safety flare on site, and then we have our pump and control room, which then incorporates our AI machine learning system to automate your plant. We then can add additional pieces of equipment depending on sort of what your site requirements are. So for this site, we had included filtration and an aerobic step because we need to discharge to watercourse. And there's an endangered snail in the local area. So we had quite strict sort of regulatory discharge requirements, and we integrated a biogas conditioning and CHP system at the facility so we could reuse the heat and the electric. So over the project, this means that there'll be 375,000 in cost avoidance for Hepworth. They could lower sort of the treatment costs by 10%. They can generate 360 megawatts of renewable energy a year, and they'll save 100 tons of carbon annually. And Andy, yeah, really found that there was a unique compact solution where they could treat all their wastewater on site, and he's been impressed with the trial. And we've now starting the installation of the full-scale system, which will be operating later this year. The next case study is Cook Foods, that you probably are all aware of. They are really sort of sustainability driven, so they have 100% renewable electric for all of their sites, and they're really focusing on reducing their absolute greenhouse gas emissions by 29% by 2030, and then they want to have carbon offsets for their direct operations. The current challenges they have is thermal energy demand again, sludge production, and wastewater management. So what we did for Cook is we did a pilot system for them as well. Here you can see the same one that was installed at Hepworth, but rebranded at that facility. So What we saw is we had quite sort of a significant fluctuation in the organic loading rate due to the variability of the COD that we were seeing at this facility. So we are having sort of the pumps for this site because the pilot system isn't fully automated. We're manually operating that system. We had really quite significant high organic loading rate, but one thing that was really good is we were consistently able to generate a good sort of methane percentage even with this variability. Some of the key insights are we found that the biogas had really low H2S within there, so it's about 300 ppm, so about half, maybe even more than what you would standard to get with an anaerobic digestion system. So this reduces sort of the upgrading and cleaning of the gas and makes it easier to integrate into boilers. The influence COD varied between 20,000 and 80,000. So this is a huge variability of the system, but we are able to provide like between 85 and 95% COD removal. And during the pilot, we've generated 157,000 litres of biogas. The project going forward into commercial stage will generate 3.4 million in savings over 10 years. It will generate 3,000 megawatts of renewable energy a year and will save 156 tons of CO2 just from the biogas. And there's additional savings as well from sort of the removed trucking and methane emissions that would come from sort of the sludge. Richard, the sustainability director, has been really impressed with the trial, started generating gas really effectively, and had really good sort of circularity and sustainability that can then help Cook move forward with their net zero goals. So together, by looking at sort of new ways of integrating technologies, we can protect our most precious resources. So if you want to join us and accelerate your next net zero journey, we are doing a BFBI exclusives open day at our office where you can come and see our research facilities, some of the lab testing that we do for our customers, and also some of the reactors in manufacturing as well. And that'll be on the 2nd of April. Thank you very much.
Thank you, Tom. Really appreciate that. I hope everyone found that useful. There is a couple of questions in the chat, Tom. One of those questions are, how much electric power does your reactor need?
Yes, so the reactor and the electrodes is a very minimal amount. So it is a few sort of kilowatts a day to run the electrodes specifically. The actual power consumption of the overall plant will vary depending on the influent temperature of the waste coming in to heat up the wastewater, depending on where we want to treat that. We can treat the wastewater from like 25 degrees to 30, sort of 8 degrees. So we have a much more sort of variability than a standard anaerobic digestion, which has to be at sort of a higher temperature. And that'll be sort of the biggest energy consumption is sort of the heating side of things. And then it would be sort of the standard like pumping that you would have with sort of any other process. So it does sort of vary, but the actual electrode part of the process is very minimal.
Real. There is another question as well. In relation to the capture of CO2, does your technology allow it to be reused in the food and beverage industry, noting the legal / quality requirements for CO2 use? This could be immensely valuable for those that use CO2 in their production, but are prone to price fluctuations due to supply and demand issues.
So our technology doesn't actually capture CO2. We're converting CO2 into methane within the biogas. So that's not something we're able to do, and we wouldn't be able to produce food grade CO2 from our system unless you had a biogas scrubbing system to take out the CO2 from the biogas. That can be integrated, but it's quite a costly piece of equipment. But I can ensure Andy will probably be able to share sort of his CO2 recovery that he has on his fermentation tanks.
Got another question here as well. Can the reactor operate at thermophilic temperatures, say 55 Celsius?
So we haven't operated the system at 55 degrees at this moment in time, but we do find that we have the microorganisms that live in thermophilic temperatures. So there is an opportunity for us to operate at higher temperatures. But we've had systems operating from We've got in the field 25 degrees up to 38 degrees, but we have had systems go down to about 10 degrees and still generate methane. So it does increase sort of the viability of sort of lower strength wastewater streams that come in at low temperatures.
Great. Is there any more questions for Tom? I know I've got a question, Tom. It's something that it's a general trend throughout these technologies is that we always ask what is sort of the minimum size of facility that can benefit from this technology and this equipment.
Yeah, so we would generally say um, if you are sort of like a brewery, about 20,000, sort of 30,000 hectoliter size in brewery in your production, if you're generating maybe like 10 to 15 tons of sort of like slurry sludge a day that might need to be get processed. But it does sort of vary depending on sort of how much you're paying for sort of your wastewater management and your wastewater haulage. For that. And we can handle sort of quite a variety of sort of feedstocks.
Amazing. We've had a couple of more questions pop up in the chat. What is the max TS percentage slurry able to be processed?
Yeah, so currently we're operating up to 7% total solids within the system.
And we've also got what's the minimum kg COD per day required to run the reactor?
So it can run on sort of very low amounts of kilograms of COD a day. So but it sort of really depends sort of the economics on sort of the cost. So we have variability in sort of the customer cost that could be paying £5 per ton of tankering all the way up to like £45 a ton of tankering. So that minimum amount really varies depending on sort of where you are on your sort of cost, because that's where you get the payback from the system. But for sort of a small site, we would say 20 meters cubed of wastewater, about 15,000 COD would probably sort of be the minimum size facility that we would have that would be viable.
Amazing. Is there any more questions? Nothing popping through the chat, but there was quite a number there that I think they were really valuable questions. So thank you. As I said in the intro, we will be sharing the slides with you. You'll have Tom's contact information as well for anyone that wants to follow up with him. And this, once edited, will be on our YouTube channel as well. So thank you to Tom for presenting today. And thank you for all joining and all of your questions. They've been really, really valuable. Thank you so much.
Thank you for the time. And if anybody wants to get in touch, please let us know.
Thank you. Thank you all. Enjoy the rest of your day.